Assalamu alaikum students, and welcome to a new lecture of engineering drawing and graphics, and today we are going to talk about GD and T, that is geometric dimensioning and tolerancing, and what are the GD and T symbols. This is another method of tolerancing your parts, and it is also uh, the most appropriate way of defining the system is the one that is defined by ASME, that is ASME 14.5, dimensioning and tolerancing. And tolerance. So this is another standard for tolerancing your parts, and these standards provide us a much more certainty that how our parts will be assembled and how will they function when they are assembled. So it gives us a lot of certainty, this standard, that our parts will be assembled appropriately and they will also function according to the required functionality that they are designed for, according to when they are assembled using these dimensioning and tolerancing standard. And that standard is the ASME 14.5, that is American standard for mechanical engineering, and the dimensioning and tolerancing standard is 14.5, and the slang term that is used for this standard is GD&T. It is also known as the geometric dimensioning and tolerancing system, but the real name that it has is ISV 14.5, dimensioning and tolerancing. So what we did, we also talked about general tolerancing. We also talked about general tolerancing that we use. For example, we saw that we have a part and that part has a certain dimension, and we said that we cannot, due to certain limitations, dimensioning the part according to its required dimension. So for us to have a margin for error, we place certain tolerances on that part. So now we have a room for error within which we can manufacture our parts. But do we have surety that when we do that, our parts will be assembled and they will function together? So it, for that purpose, we need a little more detail, a little more, let's say, attention to the detail, and for that purposes a new standard was developed so that we can have good quality products and they work according to their design standards. So the main thing that GD&T does is that it saves you a lot of money. It saves you money. It enhances your production, so it maximizes production, and it enhances the quality. It enhances the quality of your part. So this is what GD&T does. And now we will have a look at GD&T, that how it is different from the general tolerancing, and how does it control the feature, the size of the feature, and the location and the size of different parts on in an assembly, or let's say on a single part. Let's clear out our area first, and for that purpose let's look at this example. Here we have a table, and the height of this table, as you can see, is 30, and the tolerance that is given for this height is plus minus 1. So you are also seeing another, that is a note like a thing, and that is enclosed within these two boxes, and it tells you that the about the flatness. It tells you about, this box tells you about the flatness that is required for this table. So the flatness symbol is this one right here, and the flatness that is required is 0.5 inches, that the tabletop should be flat within the 0.5 inches. So this right here, this entire this is the enhanced image of this tabletop, and if we look closely to this tabletop, you can see that the tabletop is not at all flat, and this is the case with every surface that you experience that it is not completely flat, and even if it looked fine polished, even if it is a surface of a gloss of a very polished marble, it is not entirely flat. So for that purposes we need to define that how flat we need a surface to be. So for that purpose what we do, we define a form tolerance. This can be known as the form tolerance. We define a form tolerances for such kind of features, and we do that separately. We do not add them to the general tolerances that we already defined, because it will make our drawing more complex and it will make it more confusing. So what we do, we define it separately by not defining it with the general tolerancing that are already mentioned here. We will get back to that why we not do that, because it will tighten our tolerances, our general tolerances, and it will lead to more error, but we will get that to it in a while. So first of all we need to define the flatness for the surface, and that flatness that is defined is 0.5 inches. So what we do, we define an envelope, 0.5 inch envelope. So the total, that is the total tolerance, that is 0.5 inch. So this right here, these two lines represent 0.5 inch. They have a width of 0.5 inch. So the surface of this table should lie between these two lines. It should lie between these two lines. So if it is in these two lines, in the envelope, this is normally called the envelope. If it is in this envelope, the flatness, then it's okay. It's okay. But if it is not in this envelope, then it is not okay. So this is how we define different type of form tolerances, location tolerances, and profile tolerances. We will look at them in a while, and we like to enhance the quality of our part by controlling the tolerances on specific features, specific forms, and specific location of those features relative to another datum or individually. We will look at them in a while. So right now let's get back to these two. So here you can see that the height is 30 inches plus minus 1, and the flatness tolerance is 0.5. So the height of this table cannot be greater than 31, or it cannot be less than 29. You already know that because plus 1 is 31, minus 1 is 39. So overall the tolerance that is allowed to us is 2 inches. So the 0.5 inch flatness should lie between this range. Either we can have 30.5, so it's okay. We can have 29.5 or 29.7, whatever. It will be okay as long as it is in this 2 inches, but it will complicate things for us a little bit. For example, if let's say that the tolerance range is less than the 2 inches, let's say if it is 0.5 inches, if the tolerance allowed overall is 0.5 inches, for example it is 30 plus minus 0.25, that means that height of the table cannot be 30.25, or it cannot be less than 29.75. So overall the tolerance now is how much? That is 0.5 inches. That is 0.5 inches. So now things are a little bit complicated now, because the overall general tolerancing is 0.5 inches. So if we add this flatness tolerance to it, it will further complicate things, and then we will have to violate the general tolerancing. So for that purpose what we do, we define the form tolerances separately, and we define it within the limits of the general tolerancing, and for that purpose we have much more freedom and much more certainty that we are defining a correct feature and defining a feature with correct tolerancing. So now we have two type of tolerances in this one figure. One is the general tolerancing, that is for the height of this table, and the other is a form tolerance, that is for the flatness of this table. So we do that separately so that we may not confuse it, and overall the parts comes out to be according to the required tolerancing. So That's that about GD&T, and now let's move forward and look at some basics. So basically in geometric tolerancing, what we do, we use different kind of symbols to define the type of tolerancing that we are using. So in GD&T, as we already discussed, the tolerances are used to control the variation that exists on the manufactured parts. So what we do, we try to control the variation as much as we can. So for that purpose, we apply GD&T, and GD&T, as you already know, it provides us the certainty. Provides us the certainty that our parts will fit and function at assembly level. So certainty of fit and function at which level? At the assembly level. So for that purpose, we use these different type of tolerances, and the one that is very common in GD&T is the form tolerancing. And these form tolerances, as we already discussed the flatness in the previous slide, it was the type of this form tolerance that we like to see that how much a surface is flat. Then the other is the straightness. We would like to see an edge or a circular feature, that how straight it is. Then the other is the circularity. We would like to see a circular part, that how circular it is. We would like to see the cylindricity, that is related to the how cylindrical a part is. So these type of tolerances are related to the form tolerances, and you can also see their symbols. Each one have a different symbol, and this type of tolerances, they do not require any reference, that we do not need to specify a tolerance by mentioning a reference. For example, the one that was flatness that we saw in the previous slide, that we tried to control the flatness on the surface of that plate. So what we do, we used these two boxes. In the one box we do the flatness symbol, and in the other we specified the tolerance. So we didn't specify that with respect to which reference plane that this table should be flat or whatever, but we just simply specified the flatness on the surface of the table. So if I needed to add a datum, then which in form tolerance is not required, but let's say for example that I needed to add a datum, then I would say that the surface on which the table is placed is the datum for the flatness of this table. But in form tolerances, we do not use the reference surfaces. So that's why the informed tolerances, the tolerancing is identified individually on the features, and no datum surface is required. Then we have profile tolerances, and profile tolerances are used for features that have a profile like an arc or a semicircular feature. Then what we do, we define their profile, and they can be defined individually. They can be defined individually, or they can be related to a certain feature or a datum, as we said. So it can be a feature like this in form of an arc, and we can specify the line profile, as they said, by specifying a certain envelope for this profile only. We will be saying that within this envelope the profile should lie within this envelope, the dotted envelope. So that will be the line profiling of this particular feature. But then we have surface profile, that instead of a single line, we provide a 2D plane, an envelope in the form of a 2D plane. So that is for a surface profile, and for that it can be individually, or a reference might be required. Then we have orientation, the type of tolerance orientation, and it can be that the two features can be perpendicular with each other like this, or they can be angular to each other like this, or they can be parallel to each other like this. So it depends that how much these two are perpendicular, how much they are according to a certain angle, or how much they are these two surfaces are parallel to each other. So these are the orientation type of tolerances. Then we have runouts, and runouts are basically circularity and cylindricity when we are talking about, let's say, a cylindrical feature. And if we want to check the circularity of this particular cylinder with reference to the axis, the central axis that this cylinder will have. So when the reference for circularity is the axis, it is called the circular runout. When the axis for cylindricity is the axis, then it is called the total runout. So one is circularity, and for that, when we take this axis as a reference point, then it will be called the circular runout. But the other is cylindricity, and if for cylindricity, let's say we take this axis as a reference point, then it will be called the total runout. Then we have location. In location, we can have concentricity, that is used for two cylinders that we want to have a single center, and the other can be a position. It can be a position of a hole on a plate. Then we need to define its tolerance from two edges like this, and one can be this edge and the other can be this edge. These can be the two datums for this position, and the other can be the symmetry, that we want to see how a certain object is symmetrical between two other parts, that how equally divided it is. So these are the different type of tolerances that we use in. So what we use to define a certain, for example, tolerance type in GD&T, that is the SME 14.5 dimensioning and tolerancing standard. Dimensioning and tolerancing standard. We use a feature control frame, and that is a special type of node that contains boxes, and each box gives us a certain information because it's drawing, so we need a certain type of a standard to represent a certain information. So in SME 14.5 dimensioning and tolerancing method, also known as the GD&T, we use the feature control frame, and that feature control tells us different, each box gives you a certain type of info. So in the leftmost this box right here, there the geometric symbol will be present, that either we are talking about what type of tolerance we are talking about. It can be flatness, it can be straightness, it can be circularity, it can be a position, it can be parallelism, or whatever it can be type of GD&T it can be. So then we have a tolerance information, the how much tolerance we are going to define, and then we will talk about the datum surfaces in these three boxes, or it can be two boxes, or it can be one box, depending on the reference surfaces that we have. So these are the compartments that we use in the feature control frame, and we can also write them in word form by connecting these boxes. For example, we can now place a geometric symbol right here, and let's say I talk about the straightness. I talk about the straightness, or let's say cylindricity. Let's say the cylindricity of a certain cylinder. If we have a certain cylinder and I talk about this cylindricity, then it's the cylindricity of the feature must be within. Now I'm talking about a circular part, so I will mention the diameter symbol, and let's type 0.02. So the cylindricity of the feature must be within diameter 0.02 relative to, so it is a form tolerance. Cylindricity is a form tolerance, and right now with form tolerance we do not use references. So what I will do, if I need to fill the reference box, I will use a tolerance for which reference is required. So let's say I write position, that the position of the feature must be within. And now let's say the diameter is not required. Let's say that I am talking about a position of a hole. with respect to these two datums. For example, one is datum A and the other is datum B. So the position of the feature must be within 0.02 relative to datum A, B. If I had another datum, for example, let's say that the bottom surface is another datum, then I can write A, B, C, that is the primary, secondary and tertiary datum surfaces relative to these the three datum surfaces. So now I am identifying the position 0.02 relative to these three datum surfaces. So this is the feature control frame that we talked about, and this feature control frame uses different features, the different symbols that we identified in the previous slides, and here you can see that the position of a certain feature having diameter 0.03, that is the material condition. We will talk about this in the later slides, and then we mention the datum surfaces. So one is the geometric characteristic symbol, the other is the tolerance zone description, and then we have primary, secondary and tertiary datum. One is the geometric tolerance and the other is the material condition symbol. The material condition symbol is either MMC, LMC, or regardless of feature size. So this is the maximum material condition, least material condition, and regardless of feature size. We will discuss them later in this topic. And so this feature control frame reads as the position of the feature must be within a 0.003 diameter tolerance zone at maximum material condition relative to datum A, B and C. So this is what the feature control frame is telling us. So right now what we need to see is that we have two views. One is a front view, the other is the side view. So which one would you like to call? Let's say this is the front view, this is the side view of a certain feature, and you can see the feature control frame right here. You can now see the feature control frame. So what is this telling us now? And this is telling about this feature control frame is telling us about the position, that the position of this circular feature right here. You can see the side view of this circular feature, but in the front view of this circular feature, but in the side view it tells us the whole story. So in this side view, a circular feature having position tolerance. So this is the position tolerance of 0.005 diameter at maximum material condition with reference to this datum. This circular surface is the datum. This circular surface is the datum for the position of this circular feature. So here, apart from the other dimensions that are mentioned on this circular feature, for example, you can see that this circular feature has a unilateral tolerance of 1.00 and 0.9. So overall the tolerance is 0.1 minus 0.1, you can say, plus 0.0. So here it has a general tolerance, but then this feature is also positioned relative to this circular surface. So that position is mentioned separately in this feature control frame, that the position of this circular feature will be controlled with reference to this circular feature, and the overall tolerance for the positioning of this let's say we call this circular feature 1 and this circular feature 2. So the position of the circular feature 1 with respect to the circular feature 2 should be within this tolerance range, that is 0.005 diameter. For example, if you would like to draw an envelope for this tolerance zone, then it will look like this, that the position, let's say this and this right here, and let's say that this distance is equal to 0.005. So this circular feature must lie within this envelope. So this is what this feature control frame is telling us, and it must lie within this envelope relative to this feature right here, relative to this outer circular feature, which is the datum surface. This will be known as the datum because it is the reference. It can also be known as the reference, but the more appropriate nomenclature is the datum. So this outer feature, circular feature, is the datum for this smaller circular feature, and the smaller circular feature must be positioned within 0.005 envelope relative to this datum surface, that is datum A. And with the help of this feature control frame, we are now able to communicate this information. And as you can see, these are the general tolerances and these are the GD&T. This is the GD&T.